Okay, good morning, colleagues. Welcome to the International Cosmic Day. Uh, this is Kenyatta University. Today is 21st November 2023. Welcome to the International Cosmic Day. So today we are going to learn about what cosmic rays are, where they come from, how they interact, and what are the applications of cosmic rays. So the presentations will be in two parts. One part I'll give a general overview, and then the second part Ms. Veronica Nyambura will give a presentation of her work, what she has done for the measurements of cosmic ray muons in the Department of Physics at Kenyatta University. So in the first part, I'm going to talk about cosmic rays, origin, composition, interactions, and applications. So by the end of this first part, you will know the origins of cosmic rays, what is their composition, how they interact in the Earth's atmosphere, and applications of cosmic rays in various fields. So I'll talk about the discovery of cosmic rays, the nature of cosmic rays, how they interact in the Earth's atmosphere. I will also talk about the all-particle cosmic ray spectrum and some of the big science experiments in cosmic rays. And then I will talk about applications, muon tomography, muon radiography, and so on. So way back in 1909, Theodore Wolff used an electrometer, and they reported increased ionization levels at the top of Eiffel Tower, and this was higher compared to the ground level. A few years later, in 1912, Victor Hess used electrometers on a balloon up to a height of 5,300 meters above the ground, and they reported high ionization levels compared to the ground. And the origin of this ionization was not solar, it was not from the ground, and so it was named cosmic origin. And later on in 1936, he was awarded the Nobel Prize. So the primary component of cosmic rays consists of about 85% protons, 12% helium, and 3% iron. These particles interact in the atmosphere of the Earth to produce secondary cosmic radiation. And this comprises of kaons, pions, electromagnetic photons, muons, neutrinos, electrons, positrons, neutrons, and so on. So what you see on the left side is an artistic impression of the interaction of primary cosmic rays in the Earth's atmosphere to produce all these particles, which we call an extensive air shower. So in the extensive air showers, the muon component is the most robust component, and it is able to reach the ground and beyond. So on the ground level, on the surface of the Earth, you can measure the muon component as well as the neutrino component. But neutrinos have got a very small interaction cross-section and therefore quite challenging to measure, but they have been measured in neutrino astrophysics experiments. So this is what happens, for example, when a proton interacts with a nucleus in the Earth's atmosphere. You produce pions, kaons, and they decay. So for example, the neutral pions decay into gamma ray photons. The charged pions decay into muons with the emission of neutrinos. And the muons in turn decay into electrons and positrons with the emission of neutrinos. So the muon component can be measured on the surface of the Earth as well as in underground laboratories. And knowledge of, for example, the muon component enables one to reconstruct the extensive air shower and study more about the extensive air shower to know what was the primary particle that initiated the shower, what was the energy, and what are the interaction mechanisms. So there's a lot of theoretical particle interaction models that can be used to describe the interaction of these particles in the Earth's atmosphere. So here is an animation made a few years ago. What you see here is a proton coming into the Earth's atmosphere. Pay attention to the time scale on the bottom right corner. So this is at minus 400 microseconds. After 100 microseconds, the proton has already interacted and produced the secondary component. So photons have been produced, electrons, positrons. After another 100 microseconds, you see now the extensive air shower forming in the Earth's atmosphere. Another 100 microseconds, you see the extensive air shower forming, and you can see the muon component sticking out from the bulk of the extensive air shower. So finally, you have the muon component reaching the Earth's surface with sufficient energies to propagate through the Earth overburden, and you can measure the muon component in underground. So basically, this is what happens in the Earth's atmosphere all the time. And on the Earth's surface, we can measure the muon component as well as other components. So that's the extensive air shower formation. And during my PhD work, I used the Aleph facility at CERN, that is the European Laboratory for Particle Physics or European Organization for Nuclear Research. What you see here is a multi-muon event recorded by the Aleph facility. This was one of the detector stations at the LEP, Large Electron Positron Collider facility. So this was part of my PhD work. Now, having known how the particles interact, now let's look at what the cosmic rays are. So on the left side, you see the all particle spectrum of cosmic ray particles. The y-axis is a flux of the cosmic rays, and on the x-axis are the energies of cosmic rays. So the flux ranges from 10 power 5 to 10 power negative 28. So those are over 30 orders of magnitude. And the energy scale is from 10 power 8 to 10 power 20. So those are over 10 orders of magnitude. And at low energies, you've got cosmic ray particles hitting your detector on average 1 particle per square meter per second. As the energy of the cosmic ray particles increases, you have 1 particle per square meter per year. This is typically at 10 power 15 electron volts. Further on that spectrum, we have ultra high energy cosmic rays, and the kind of flux is approximately 1 particle per square kilometer per year. And it's amazing that this all particle spectrum is described by a simple power law where the flux is proportional to the energy of the particle raised to negative gamma. Gamma is a spectral index. It changes at about 10 power 15 electron volts. That's the region we call the knee. And at about 10 power 19 or so electron volts, that's beyond the knee. It changes to 3.1. So there's been a lot of experiments to investigate this ultra high energy cosmic ray particles. So one of them is the Auger experiments. That's the world's largest astroparticle physics experiment. And they're looking at the ultra high energy region of cosmic rays. So the changes in the spectral index are related to the chemical composition, maybe possibility of maximum acceleration achieved, or the GZK effect. This is the Greisen-Saseptin-Kuzmin effect. I'll talk about this. You're probably wondering, what are these fluxes all about? 1 particle per square meter per minute or per year and so on. So to put things into perspective, I've fished out the image of the stadium during the last World Cup. So if you assume the field of play 110 meters by 75 meters as your surface area of your detector, And if you assume the duration of the match 2 times 45 minutes, then you would expect at least one particle with energy above 10 power 15 electron volts for that detector surface area and for that duration of data collection. So in a duration of a typical match, you expect just of that kind of energy. So we call it the knee because there's a change in the spectral index. So this is an image of the human leg, and on top of it, the data is superimposed, and the data is scaled to energy raised to 2.5, so that we see the changes in the spectral index. So at about 10 power 15 electron volts, or 10 power 6 to 10 power 7 GeV, there is a visible change in the spectral index from 2.7 to 3. So that's the region we call the knee on the all-particle cosmic ray spectrum. And beyond the knee, it changes to 3. And then way beyond 10 power 19, 10 power 20 electron volts, we have the ankle on the spectrum. So scientists still don't know where there is an end to the spectrum on this. So the origins of these kind of phenomena could be galactic leakages, maximum accelerations, or some unknown effects. On the knee, there is the famous polygon atom model. That means the composition of cosmic rays is varied. Particles of different masses, protons, iron, carbon, helium, and so on. So they lose energy in different ways, and it leads to changes in the spectral index. So for the GZK effect, if you consider, for example, protons interacting with photons of the cosmic microwave background radiation, they would undergo losses in energy via photopion production or pair production, and thereby losing large fractions of energy. So protons interacting with photons of the cosmic microwave background to produce pions, that's photopion production or pair production. So in these processes, they lose a lot of energy. Heavier nuclei can suffer photodisintegration. So this is the equation. A heavier nucleus interacting with cosmic microwave background radiation photons to disintegrate into lighter ones, or also pair production. So these processes lead to drastic cutoff on the cosmic ray energy spectrum at those energies, and these are known as the GZK cutoff, named after Greisen, Zatsepin, and Kuzmin, the scientists who formulated this. Next, I will describe our work on cosmic ray muons. As I've said, I measured cosmic ray muons using the Aleph facility at CERN. That is the world's largest particle physics experiments. So one of the detector stations was Aleph during the LEP. That was a Large Electron Positron Collider facility. And it was built for collisions of electrons and positrons. And one of the channels is muons, mu plus and mu minus. So the detector facility was capable of measuring muons. So the science goal for my work was the measurement of the momentum spectrum and charge ratio of cosmic ray muons. And as I said, we use the Aleph. It was located at 140 meters underground. That corresponds to 320 meters water equivalent. And we also did some Monte Carlo simulations of extensive air showers using Corsica and the propagation through the overburden, and the detector was carried out using GANT simulation package. So here is an image of the Aleph facility. As I said, it was built for E plus E minus physics, and one could also produce mu plus and mu minus. So the innermost was the time projection chamber, and then we had the electromagnetic calorimeters, hadron calorimeters, and the outermost were muon chambers. So the muon chambers served as positive identification of the muon from cosmic rays, and we used the time projection chamber to measure the momentum spectrum of cosmic ray muons. Uh, this is what we observed. The red data points represent our measurements in Cosmo Aleph, that is way back in 2007. And the other data points are shown here, and our data was consistent with previous measurements, as well as the parameterization at that time by Hebeck and Timmermans in 2002. And for the charge ratio, this is the ratio of mu plus to mu minus. We compared our measurements in red dots with previously reported measurements at that time in 2007, as well as the parameterization by Hebeck and Timmermans shown on the black solid line with the error margin shown as a yellow band. So we also compared with Monte Carlo simulations using COSICA, that is the cosmic ray simulation for Cascade experiment. That was the leading experiment at that time for measurement of cosmic rays at the region of the knee. So the different models for cosmic ray simulations are shown here. Those were the models that were available at that time. And the data was consistent with the models. But some of the models overestimated the charge ratio, others underestimated, but all in all, it was a good comparison. So in addition to the momentum spectrum and charge ratio of cosmic ray muons, I also looked at the cosmic ray intensity at underground. And here you see the variation of the cosmic rays with zenith and azimuth angle. And you can see because the detector was cylindrical, you could see the effect of the cylindrical shape of the detector. And you see more muons through the voids of the detector. And you also see muons being chopped off in the direction of the Jura Mountains. So this was particularly interesting for low energy muons. For high energy muons, you could not see this. So this is like a muon tomography. You see underground structures, and I'm going to talk about this later. So that was based on my PhD work way back in 2007. And then later on, I supervised students at Kenyatta University. This is a sample work by one of my former students, Mr. Livingstone Ochilo, now Dr. Livingstone Ochilo, who went on to do a PhD in this field. So this is what he observed at that time. He carried out Monte Carlo simulation of extensive air showers and saw the east-west effect. Basically, these are muons, they are charged, and therefore, as they propagate through the Earth's atmosphere, they are affected by the Earth's magnetic field. So charged particles in magnetic or electric field will be deviated. And you see more particles from one side compared to the other side. And this was observed using Monte Carlo simulation. And as I said, Dr. Livingstone Ochilo went on to do PhD at Zigen University, where I did my PhD. And he's currently back to the country and serving at Jaramogi Oginga Odinga University, and also helping me in co-supervision of students. This is another work by my student, Namasaka, in 2011. He was looking at the charge ratio of cosmic ray muons at high energies and looking at the contribution of the kaons, because kaons are heavier than the pions. So you have more energetic muons coming from the contribution of kaons. So Namasaka is also doing his PhD in Germany. And later on, I've been working with more students in this field. Here is a summary of what they have observed. The students are the late Penina Mugo, Samuel Buruchege, both supervised by Dr. Naftali Kimani in our department and Dr. Livingstone Ochilo, with the advice of my PhD supervisor, Professor Klaus Gruppen. So basically what they did was to measure cosmic ray muons as a function of zenith angle, and they found the measurements to be consistent with cosine squared of the zenith angle. And they also measured the lateral distribution of cosmic ray muons, and the data was consistent with NKG function. This is Nishimura Kamata-Greisen function. So these preliminary results were presented during the African Physics Society meeting during COVID. That was in November 2020. And we are still doing this kind of work using the plastic scintillators, the photomultiplier tubes, sodium iodide detectors, and the NIM electronics. So later on, my current student, Miss Veronica Nyambura, will update you on her results. Now we can switch from fundamental physics to applications. So the first application that I would like to talk about is the cosmic radiation in the aviation industry. Now that we have seen the occurrence of cosmic rays in our atmosphere, and these are charged particles, and they would contribute to the human exposure to cosmic radiation. So on the left, you see a plot showing the variation of the vertical cutoff rigidity as a function of geographic positions. So the red line shows the geomagnetic equator, and the green line shows the geographic equator. Now, the contour lines that you see are the vertical cutoff rigidity. This is a measure of how strong the magnetic field shields us from charged cosmic rays. And as you can see, in the region of the equatorial region, the cutoff rigidity is maximum, and therefore you have maximum shielding of charged cosmic rays by the Earth's magnetic field. As you move away from the equator, the cutoff rigidity reduces drastically. So if you look at the northern hemisphere, there's a great reduction in the cutoff rigidity, and therefore more cosmic rays come to the regions outside or far off from the equator. Now, on the right side, you see the effective dose rate as a function of geographic latitude. And you can observe the minimum dose rate near the equator. So there are different curves for the dose rate depending on your flight altitude. So the lowest curve is 20,000 feet. There is hardly noticeable variation in the dose rate. But as you fly high up in altitude, the dose rate is significantly different depending on your geographic latitude. So if typically you fly close to 40,000 feet for commercial flights, you can see at the equator, the dose is approximately 3 microsievert per hour of flight. And at high latitudes, maybe plus or minus 60 degrees, north or south, the dose rate is 3 times that much if you fly close to 40,000 feet above the ground surface. So at the equator, it's about less than 3, and at 60 degrees north or south, it goes to 7 or so microsievert per hour. So here is another plot that shows you the same situation. Near the equator, you've got low dose. Away from the equator, you've got high dose. 2 to 3 times higher than what you receive at the equator. This is true for commercial flights. Now, for space travels, maybe higher than 40,000 feet above the ground surface, there is a significant increase in the dose. So for this reason, we all need to know what cosmic radiation is and how it affects how our dose. But fortunately for normal flyers, this dose would not cause any problem. This dose is a problem for the aviation workers, the flight crew, that means the pilots and the air cabin crew. And we need to regulate this exposure, as you can see from this kind of a plot. So to put things into perspective, here is another plot showing you the different regions. So region 4 is near the equator. This is where you have the lowest dose. If you fly 40,000 feet and above, and then followed by region 3, and then region 1, you have the highest dose. So you can see where region 1 is, the northern hemisphere and extreme southern hemisphere. So if you fly in the northern hemisphere, you get more dose due to cosmic radiation as compared to flights within the equator. But this should not worry you. If you're a business traveler or something, you're not considered as a radiation worker and your dose will be minimum. And there are online tools as well as offline tools to monitor your dose. And the considerations are flight routes. That means, are you flying in the northern or southern hemisphere? Are you within the equator? What is your duration of your flight? And also the condition of the worker. So this is cosmic radiation. It needs also to be regulated. And I'm pleased to share with you all that in Kenya, we have adopted ISO standard for regulation of exposure to cosmic radiation. So this is KS ISO 2785 series. It comes in several parts, and the Kenya Bureau of Standards has already adopted this standard, and the next step would be to implement this standard for the aviation industry. More applications of cosmic rays are in the fields of engineering. That means civil engineering, underground applications, industrial applications, muon transmission, radiography, volcanology, archaeology, security applications. That means border control and facilities. You can use cosmic ray muons to image this. You can also use them for nuclear waste characterization and also nuclear safeguards and materials control. Yesterday, we had a very interesting seminar on muon tomography by an expert from France. And these are some of the applications you can find in muon physics. So I've done a screenshot of an IAEA technical docs 2012 on muon imaging. It describes all these applications, including the theoretical framework. So if you're interested, you can read more about this applications. So muon tomography basically is based on scattering of the muons. The heavier the target material, the higher the Z or Z of the target, the more the muons are scattered. And this forms the basis of muon tomography. So we make use of muons and how they are scattered, and you can distinguish between the chemical composition of your absorber. So that means where there are voids, you get more muons. Where there are heavier elements, you get muons more scattered, and so on. So the basic idea is to use cosmic ray muons to image large-scale structures. This includes mountains, pyramids, volcanic mountains, and so on. And the aim is to understand the hidden structures of these facilities and also to map resources. So I'm pleased to share with you that we are forming a group together with Water Resources Management in Kenya to utilize this kind of technology to image our water resources. And I think this week there's a team that is going to Chulu Hills to map or to understand how the resources can be mapped using cosmic ray muons. So here is also another artistic impression on how you can use cosmic ray muon beam going through a pyramid. And on the other side, you put some muon detectors. And these detectors will give you the internal structure of a pyramid. So where there are voids, you can discover previously unknown chambers, the king's chambers, the queen chambers, and so on. So cosmic ray muons provide you with a means of non-invasive, non-destructive imaging technique, because cosmic ray muons are there. It's a beam of particles that is available 24/7 every day throughout the year and so on. So the changes in density, the different materials, the voids can be seen using cosmic ray muon detectors. And at Kenyatta University, we are developing this capacity at the national level. So our electronics and instrumentation team are partnering with an expert from France in order to have the technology transfer, the knowledge transfer, so that we start building prototypes of this kind of work. So in muon radiography, again, you can use muons and sets of detectors to image cargo in containers that comes in through our borders in a very effective, non-invasive way, very passive way. You're not using a source of ionizing radiation, you're just using muons, and how they are scattered gives you information on what is inside the containers that are finding their way into our country, or whether final destination is here or whether they're in transit. So you can use muons, and this idea is welcome. So thank you very much. That is what we have for the first part of this session. Do you have any question? The second part will be more technical, where Monica Nyambura will give us a talk on her current results. Yes, I can see a hand raised by Dr. Naftali Kimani. 1 minute, let me. Wait a minute, Dr. Naftali Kimani, we're in the lab and we are projecting on the TV. So we want to increase the volume on the TV so that the audience in the lab can hear you. Please go ahead with your question.
Thank you very much, Dr. Hashim, for the exciting presentation or a talk. But I wanted to ask probably two quick questions. I wanted to understand, now that the muons generally don't have effect on humans as they transfer, then what will be the effect of long-term exposure to the humans, if any, to justify the concerns in the aviation industry? And the other one, I wanted to understand with the effect of the global warming. I would assume that we have, increased CO2 in the air, and these particles, due to the increase in temperature, they will be in a high kinetic activity or kinetic motion. Would that in any way increase the interaction between the primary particles with the CO2 or other particles that are there, resulting to a bigger shower? Or in other words, can we use the muons in any way to monitor the global warming effects? Thank you, Dr. I don't know if
my explanation. Sorry, my microphone was off. Sorry about that. My microphone was off. So I said, thank you very much, Dr. Naftali Kimani, for that question. Your two questions are on long-term exposure to cosmic radiation. I think just leave it like this. Yeah. So the first question was on long-term exposure to cosmic radiation, and the second one on impacts of cosmic rays on global warming. Yes, cosmic rays are ionizing radiation, and the dose increases with altitude above the Earth's surface. It also increases with latitude. The farther you are from the equator, the higher the dose. And as we have seen in those plots, I'll try to share them once again. As we have seen in those plots, there is need to regulate the cosmic ray exposure, especially for the aviation workers. So there is some restriction on the flights, routes, as well as the flight durations. So aviation workers are monitored for their cosmic ray dose. And once they reach the limit, the annual limit for radiation workers, they are rerouted and or they are simply grounded. So I'm happy that in Kenya we have adopted the ISO standard for regulation of human exposure to cosmic radiation. So, and I said the considerations are the flight routes. If you fly in the northern hemisphere at high altitudes, you get more exposed to cosmic radiation as compared to flights near the equator. Other considerations are the condition of the worker, the age of the worker, the gender, and the general medical condition. So yes, long-term exposure may be harmful, and for that reason, it has to be regulated. And as I said, we have adopted this standard in Kenya, the ISO standard 2785 series, and the next would be to implement it for our aviation industry. The other question was about impacts to global warming. There's been some studies that link cosmic ray intensity with ozone layer. So as you know, when the ozone layer is depleted, you have global warming increasing. And that is one link between cosmic rays, ozone layer, and global warming. So there was an experiment, cloud experiment at CERN, that was carried out to carefully understand the mechanisms of cosmic ray interactions, the Earth's atmosphere, and the ozone component. So I'll fish out some of this information and show you in the course of the day. Any other question, either online or offline? We have participants who are offline. They're here in the lab. Okay, so there's a question from our chairman. He's basically asking why cosmic rays flux or dose differs with latitude, the farther you move from the equator. Okay. I will share these slides once again and talk more about the rigidity, the ability of our atmosphere to, or the magnetic field of the Earth to shield us from charged cosmic rays. So if you look at this diagram, the left side, this is the vertical cutoff rigidity. The numbers represent the ability of our magnetic field to shield us from charged particles entering our Earth's atmosphere. So the red line is the geomagnetic equator, the green line is the geographic equator. Now the contour lines that you see with numbers indicate the rigidity. And as you see near the equator, the numbers are highest, 17, 16, 15, 14. So that means near the equator, you've got the maximum uh, shielding effect, because the Lorentz force for charged particles in magnetic field varies with cosine of theta. And the magnetic field lines near the equator are almost parallel to the Earth's surface. And most of the cosmic ray particles, the majority are vertical. So vertical cosmic ray particles entering a magnetic field perpendicularly, because of the cosine theta, you have got the maximum shielding, the maximum force the particles will experience. So that is why you've got the maximum cutoff rigidity near the equator. Far away from the equator, the magnetic field lines are no longer parallel with the surface of the Earth. They're inclined, and therefore the resistance is minimal. And that is why you've got higher dose far from the equator compared to minimum dose near the equator. So it's more of the interaction of a charged particle with the Earth's magnetic field and the angle of inclination. Near the equator, the magnetic field lines are almost parallel and the particles are almost vertical. So when they enter, they experience the maximum force, the maximum Lorentz force, because of the cosine theta dependence. Away from the equator, theta is no longer 90 degrees, so you've got minimum force. So that was the question by Dr. Nyenge, our chairman. I can see there is a hand raised by Flavius Kubli. Please go ahead. Flavius Kubli. Flavius Nkubi, please go ahead and raise your question.
Can you hear me? Yeah, I was trying to ask. I was trying to ask about the medical applications of muon radiography. I don't know if I missed that out during your presentation. Can you please shed more light on that?
Okay, thank you very much for that question. It's on medical applications on muon radiography. Um, muons, cosmic ray muons, can be used to image structures. And as we have seen yesterday in the seminar on muon tomography, you can image very large structures, large scale structures like pyramids, volcanic mountains, and so on, to very small components, electronic components. You want to see the structures. So medical applications is not yet thought of, is not yet applied, because we use ionizing radiation to image human subjects. But in principle, if you put a human target and below it you put the detectors for cosmic ray muons, in principle, you should be able to see some image of the human body in principle, but it has not attracted a lot of attention because we have already existing imaging techniques which perform very well.
Thank you.
I think the issue is the resolution of muon tomography. Yeah. It's a bit lower than that. Yes. Existing equipment for medical applications. Yes. Yeah. So another contribution from our chairman, Dr. Nyenge, is that the issue that, as we have seen yesterday, for muon tomography, the resolution is low compared to existing conventional techniques for medical imaging. So X-rays, gamma rays, and other techniques, MRI and so on, they offer higher resolution than the muon tomography. So for that reason, muon tomography or muon radiography has not attracted attention in the medical field. Not yet. Maybe in future we have high resolution detectors for cosmic ray muons, and it will be very interesting if we can image human subjects without exposing them to highly ionizing radiation like gamma rays, X-rays, and so on. And as a challenge was made yesterday, if we can come up with a source of muons, then it will be very useful for imaging, also in medical applications. So any question offline in the lab? We have the Kenyatta University physics students are here, some fourth years, some postgraduate students are also here. So feel free to ask a question. If not, then we proceed with the next presentation by Veronica Nyambura. She will talk about her work for her MSc. So please go ahead, Veronica.
You have to share the screen. Okay.
It's okay.
Mm.
Okay, just rotate it here.
Okay.
Okay, just move your slides here.
Good morning, everyone. I'm Miss Veronica. I'm presenting the research that I've been doing on cosmic ray muons, and particularly I've been working on the lateral distribution of cosmic ray muons. When we speak of lateral distribution, it's more of the horizontal distribution of cosmic ray muons. It can either be a lateral distribution or angular distribution. So, what are cosmic rays? That might hit on you. What are cosmic rays? How do they interact with the atmosphere? So, on our left side, we have the EAC, the extensive air showers. It shows the formation of the extensive air showers, and we have a proton that interacts with the atmosphere to produce secondary particles. We have the first interaction. From the first equation, the proton interacts with the atmosphere to produce charged pions and neutral pions. The neutral pions, they decay to gamma rays, and the charged pions, they decay to muons. And then finally, these muons, they decay to electrons and positrons and antineutrinos and neutrinos. So what have I done? Particularly, I have done measurement of cosmic ray muons using twofold coincidences. Uh, you might think, why do we use coincidences for the measurements of cosmic ray muons? The purpose of use of coincidences is one, uh, if you measure muons just using a detector, you are likely to get all the particles from the atmosphere. But when you use coincidences, you get rid of the false coincidences, which might arise from the gamma from the ground or from the wall, or the potassium 40 that may arise from the wall or from the ground. Okay, from what you can see 4 detectors and 3 AND gates and a counter. So for this research, we have used 4 detectors. So why are we saying this is a twofold coincidence? It's a twofold coincidence because it involves 2 detectors in coincidence and other 2 detectors in coincidence. So our final coincidence will be in the third AND gate, uh, which is finally counted in the counter. Why use AND gates? AND gates, they ensure that you have to have account on both sides. There have to be account for the 2 detectors and another count for the 2 detectors for you to have a final count. What if we get a detection from from one of the 2 detectors and there is no coincidence in the other side for the 2 detectors? We will not have a coincidence. So this ensures that there is a very clear signal for the muons. So we varied our distance up to from 0 to 35.5 meters. We power these detectors to 950 volts. And then after you power the detectors, you connect to the amplifier for the amplification of the signal. And then you connect to the discriminator so as to remove noise. And then finally, the output is fed to the quad coincident at gate session. And then the counts are counted at the counter. Then, as you can see, there is a graph we have there showing us the results that we have obtained. And we have a graph showing the lateral distribution of the cosmic ray muons. We have used the NKG function. The NKG function is the Nishimura-Kamata-Gressen function. It shows the lateral distribution of cosmic ray muons. As you can see from the graph we have, our data is consistent with the NKG function, and the equation is shown. A is the normalization factor, R naught is the Monera radius, B and C is the shower edges, and then we have this shows all the data that we have obtained for the twofold coincidences. Then we have done simulations. You have different models that you can use for the simulations. Particularly, I have used Apple's LHC. A colleague have used DPM Jet. He's called Samuel Bolochege. When we use the Apple's LHC for the simulation, above there you can see the graph showing a combination of the simulation. As you have heard, we have 85% protons and we have 12% helium, and then we have ion 3%. So for me, this graph shows a simulation for 100,000 showers, and for these 100,000 showers, I have ensured that the 100% represents all the whole particles, all the particles that we need. And for proton, when we take the 85% for the 100,000 showers, we have 85,000, helium 12,000, and ion 3,000, summing up to the 100,000 showers. And then finally, now these data have been compared to the measured results using the twofold coincidence. So the results that we had after the measurement, we take the simulation and we compare directly. So the red dots you can see, those are the measurements for the twofold coincidence, and then the black curve, it's the direct result from the graph that is above there, and it's a direct compare. Also, when you compare direct, you can see that there are some points that are aligning with the data that we have from the simulation. So it shows that our data is consistent with the multi-carol simulation done. It is consistent. Okay. And then there is something you can note that below 10 meters, there is a bit of scattering. Okay, the shower call the shower call is known to be 10 meters. So along the shower core for the EAC, there are multiple scattering there. There are many interactions there. That's why there is a bit of scattering below 10 meters. And then it shows that the work we have done implemented is correct to the physics that we have run, particularly because we from the NKG function, we have a lateral distribution, and our measurement aligns with that. Again, I have not particularly put it in the presentation. As you have heard from Daktari, we can go back to the shower and particularly learn the percentages of the particle, of the initial particle. I've also done that, and I have attained 85% that of proton with a plus or minus 24% and a bit of high uncertainty. And then I have obtained for the helium 13% plus or minus 3. And then we have 2% plus or minus 1, that one for iron and heavier metals. So when you do this experiment using the simulations, you can be able to go back and know what is these primary particles that were involved in the interactions. Okay, those are our facilities, and what we do particularly. As you can see from the picture, and they are taking measurement. A colleague of mine called Jack is taking measurement. He's planning on working on the azimuth angles of the cosmic ray muons. And from the corner, you can see we have the Shironka tank, and we have two detectors mainly for what you can see from here. But for me, mainly I have worked with 4. And as I've told you, there is something we call angular distribution of cosmic radions. You can see the board that is on that is brown a bit with different angles. That is the one that was used for the measurement of the zenith angles. And then you can see at the center there is a equipment. We call it the nuclear instrument module. This nuclear instrument module is the one that is used for the measurements of the cosmic radions. And above it, we have designed it in a way that we have the power supply above it, and then we have the power divider. So those are our contact Dr. Hashim's contact, my contact, Samuel Mbolo Chege contact, and then Jack Kisingu contact. Any questions are welcome. Thank you. Okay. Do you have any questions online?
If there are no further questions, then we will use the phone to show the next part. Now Veronica will take us through the instrumentation. I think you can see that is the instrumentation that Veronica is using. Jack and Veronica. Jack, you can hold this. Let me have the mic. Okay. So Jack, you can hold, okay. Hold this. The online people can see there. The rest can turn around. Yeah. Explain the detectors. Yeah. Start from the detectors and then the instrumentation. Okay. Got scintillator detectors here. Scintillator detectors, the instrumentation, the sodium iodide detectors. Hold it steadily. Yeah. Okay. You can basically start with the plastic simulators. These are plastic simulators that have been used for the measurement of the zenith angle. We vary the zenith angle for you to know the angular distribution of cosmic ray neon. So like now we can vary these to 80 degrees all up to 0 degrees. So basically this instrumentation is for the measurement of the zenith angle and the angular distribution. So we have another instrumentation here. This instrumentation involves a power divider. This is the power supply that I was saying. And this is the nuclear instrument module, basically. As you can see, you can just see many cables connected, and it requires a bit of cabling. We call these coaxial cables. This is the first part. We have the amplifier. Okay, so first, you can see this instrumentation. These are 4 detectors. We have to this side
and other 2 detectors that side in coincidence. So all those 4 detectors are powered to 950 volts equally. They are sodium iodide detector. They are solid incinerators. Okay, you may ask, how do these detectors work? Okay, so first we have the heat on the incinerator where there is it's grayish, and when it hits there, it is detected by the sodium iodide crystal, and then from there, it hits the photocathode and the photomultiplier tube, where it is changed to electron or to an electric pulse, and then it's accelerated at the diodes and up to even a million electrons, higher level of electrons. And then finally, the signal from this detector is connected to the amplifier for amplification. From the amplifier, now this is what we call the amplifier. It's in the nuclear instrument module. The nuclear instrument module in full, we call it the NMMI. I'm saying it in full already. So the amplifier, then to the discriminator so as to remove noise. You can see, yeah, here we have the discriminator. Yes, then to the quad coincidence. As you can see in the quad coincidence, there is either an OR gate or a NAND gate. We opt for a NAND gate because we require coincidences. And then finally, we connect to the counter. You can see there are counts. We have 83 counts from when we started learning it. And then we have a timer. It's 4,000. More than 4,000 seconds are passed when we have been learning the experiment. So I can now explain the twofold coincidences. So as you have seen in the quad coincidence, we have 3 sections. We have the first AND gate, the second AND gate, and the third AND gate. So first, if there is a coincidence in these 2 detectors, and there is no coincidence in those 2 other detectors, most likely we will not have any counts. Then, if we have a count or a coincidence in those 2 detectors on that side, and there is no any coincidence in this side, we will not have a count. So we have to, the counts that we are taking is ensured that there is a coincidence in these 2 detectors, and those other 2 detectors for us to have a final twofold coincidence. Then here we have the Shironka tank. This is the Shironka tank that is used also for the detection of cosmic ray muons. It's differently you fire it, and then if a cosmic ray is detected, you see a blue color. Okay, so I think we are good. If you have any questions on the instrumentation, you're free to ask. This one here.
You've said that they are made of. You've said that they are made of sodium iodide crystal. Okay, I'm just asking, why is it that in the detectors you are using sodium iodide crystal to detect the neon? Okay, I can answer that. Just focus. Okay, so we make use of detectors to detect the presence of ionizing radiation, because ionizing radiation cannot be measured or seen with our normal senses like sight, touch, taste, hearing. Okay, we cannot detect the presence of ionizing radiation, so we make use of detectors. The sodium iodide detector is one of the detectors that is used to detect ionizing radiation. Basically, what happens is when ionizing radiation goes into the detector, the material, the sodium iodide, scintillates. Scintillation means it produces light. Now, that light in that material is converted into electrons, and the number of electrons is amplified or increased in magnitude so that it can be processed as a pulse. Yeah. So anytime ionizing radiation goes into the scintillator material, the sodium iodide, it scintillates, it produces photons of light. Those photons of light are converted into electrons, and then there's a series of diodes to amplify the signal and then be able to process it. Good question. Any other question from the audience?
Yeah.
The terrain for water tank and this instrumentation detectors, can they work in harmony? And if not, how can you observe or record the cosmic ray muons using the Terenko tab, even to graph them, since there is no particular screen I can see compared to this? That's my question.
Okay, I will answer that. Let me come here. So, the Cherenkov tank is a steel tank. It is filled with water. When cosmic ray muons go through this tank, the water inside radiates. It produces Cherenkov radiation, what Veronica said, faint blue light. Okay, Cherenkov radiation is produced because of the electromagnetic shock waves that are generated in the water. There is water in this tank. Passage of cosmic ray muons. Muons are charged particles. Anytime a charged particle enters a dielectric medium at speeds greater than the reduced speed of light, the medium gives off faint blue light, named Cherenkov radiation, after the scientist Cherenkov. Are you seeing the tank? Yeah. Have you understood the Cherenkov effect? So anytime you've got a charged particle entering a dielectric medium like water, water is a dielectric medium, isn't it? So the passage of a charged particle faster than the speed of light in that medium causes electromagnetic shock waves, and thereby the medium now radiates faint blue light, which we call Cherenkov radiation. So the effect was discovered by Pavel Cherenkov, and they got the Nobel Prize for it. And that's why you see in a nuclear reactor, the water is bluish. That is Cherenkov radiation. Fast-moving electrons causing faint blue light to be emitted. So that's a technique that we can use to measure cosmic ray muons. What is the speed of light in water? You know the refractive index for water? Approximately 1.4. So light reduces to C over n. The speed of light in vacuum is 3 times 10 power 8 meters per second. In water, light slows down to C over n. 3 times 10 power 8 meters per second divided by 1.4. So light slows down. When charged particles travel in water at speeds faster than the reduced speed of light, that's when we have emission of Cherenkov radiation. And that's the technique that we use using this tank. So what you have here is a tank filled with water, and below the tank we have photomultiplier tubes, which detect the faint blue light, the faint Cherenkov light. So these photomultiplier tubes, in coincidence with the plastic scintillators, we put a plastic scintillator on top and another plastic scintillator below. They are in coincidence with any one of these photomultiplier tubes, you have detected cosmic rays. So the plastic scintillators are here at the moment, mounted on this experimental setup to measure the variation of cosmic ray muons with zenith angle. So in a telescopic arrangement, we put plastic scintillators on top, one here and one below. If they're in coincidence, that's twofold coincidence. If they're in coincidence with the photomultiplier tubes, then you're sure it's a cosmic ray muon that has gone through this tank. And it's a unique facility in this part of sub-Saharan Africa. There is no other university in this part past in South Africa which has got this kind of capability. Does that answer your question?
But what about the numerical values? Yeah.
Numerical values.
Now, the measurements using, for instance, you can see this, you can see the values.
Yeah. You'll also see the values. Yeah. You can zoom in here. As Veronica has said, this is the electronics modules. You capture it like this. Yeah. So these are the electronic modules. The signal from the detector is fed in here. There's an amplifier. And then from the amplifier, it is fed into the discriminator. Discriminator cuts out any noise. And you just want pulses. Now from the discriminator, it goes into the logic gate and OR gate, 1-fold, 2-fold, and then from the logic gate to the counter. Now between the time Veronica was speaking and now we have one more count. It was 83 counts, now we have 84. And we have the time over there. So if we divide this, we'll get an estimate of the count rate. At what distance are the detectors? You can put the camera like this. It's about 1 meter. It's about 1 meter. So 84 counts divided by 5,000 seconds, roughly 5,000 seconds. So these are the two detectors here. There is one detector here and another detector over there. That is the first coincidence. There's a detector here and another detector there. Another coincidence. And then the two-fold coincidence is when the 4 detectors are all in coincidence. That's what the monitor is measuring to estimate the lateral distribution. And as I said in the previous talk, the lateral distribution enables you to understand the extensive air shower. And you can reconstruct the extensive air shower and be able to, learn more about cosmic ray interactions in the Earth's atmosphere. Any questions so far? Yes.
We have 2 pairs of detectors, and we've been told that in a case where only one pair is obtaining a signal, we will not be able to find the signal detected on the final detector. So, under what circumstance do we try to have a signal from one pair? Is it when the pair is faulty, or when the signal is not strong and detected by the both pairs of detectors?
Okay, good. Veronica, have you understood the question? Do you want to give it a try or I answer? Start from this question.
You have asked a question on how the detection, why there is a detection in one of the sides of both coincidence and there is no detection on the other side. Okay, as you have seen, it's an extensive air shower, and we are sure that there have to be accounts in these 2 detectors and the other 2 detectors. So, as you have seen, it's an extensive air shower. What do you understand by a shower? When you understand by a shower is particularly when you're using a shower, as you move away from the shower, what happens? The water reduces. Is it same as what you do when you move away from the detectors? So, if there is a detection here, then the shower is different and it's spread. And you have spread these detectors in a different shower. So the muon, it means it's not from the same shower. So we want to detect muons that are from the same shower. So there can be a muon detected that is not from the same shower from these 2 detectors, and from the other detectors, there is no any muon detected. So the coincidences ensure that we detect muons from the same shower. Is it well?
So in other words, you want muons being detected in the 4 detectors in coincidence. That means you've got a muon through these 2 detectors and another one through those 2 detectors. 2 muons happening at the same time within a time window of a few microseconds. two muons coming into the two sets of detectors happening in a time window of a few microseconds or a few nanoseconds. Coincidence. As Veronica said, you have got a muon on two detectors and another muon on two detectors. They come from the same shower. And that lateral distribution enables you to reconstruct the whole shower and be able to tell what is the primary particle that caused the shower and what is the energy of the primary particle, and so on. As we said, 85% are protons, 12% are helium, another 3% is iron and other heavier elements. So you want to reconstruct that shower and be able to estimate the primary chemical composition of the extensive air showers. So the coincidences can be as much as 1 kilometer apart. So the next improvements would be to develop detectors with their own readouts, and then you do the analysis offline. At the moment, it's all hardwired, and she has varied the distance up to 30 meters. So we are basically within the shower core. But in future, we want to have detectors, data loggers, store the data for offline analysis. So that means the muons will be recorded with their own timestamps. And then you can do correlation, you can do coincidence work as other people have done. Coincidences of several kilometers. So imagine in campus here, if you put detectors in physics and other sets of detectors in the School of Engineering, that's about a kilometer or so away from here. And you detect the muons in coincidence. That can give us very good insights. So that's a challenge to the students. If you can develop some data acquisition system with data loggers, and we record the muon events with timestamps, and the timestamp has got to be accurate to the order of nanoseconds or picoseconds. So fast electronics. There is a question. You can focus on it. Oh,
Final question. Because the showers are from the atmosphere and the atmosphere's condition change with time, day and night. Is there a specific time when the showers are more and they vary, and they vary, or they are just from morning to the next month?
Veronica will give you that.
I've done some work on our evaluation, and particularly, you don't access the same muon count at the same time of the day. Okay, so at different times of the day, you are seeing different count rates. Okay, at different times of the day, you are seeing different count rates for the muon class. So you might find, like from what I have done, I took some measurements up to 8 p.m. You could find at 8 p.m. you could have the lowest number of counts. Basically, it's because maybe of the cloud cover is affected by the atmospheric pressure, atmospheric temperature. We have the solar magnetic field, we have the earth magnetic field. There are many things that impact the measurement of cosmic ray muons. So particularly, you cannot ascertain that you have the same number of count rates of the muon within the day. It varies with season. There are 3 types. There is a 11 and 22-year cycle, and there is a 24-day cycle for the duration, and there is the lunar variation, and I've focused particularly on our variation. And if you're interested, you can work on the lunar variation tonight. If you have to get catalogs, and you can work with them for the 24-day cycle. I answered.
Okay, thank you very much.
Yes.
There's a question.
Yes. I have this some data challenge. So now from the counter, what indicates that there is one muon from the two detectors, and then there's another new one because I can see two readings. I can see the first reading on top, and I can see the third. Where's that? Like the one for it, is it 1,000?
No, that is a zero.
Okay.
It's just
So
it
does that counter like make you know that there's a new one two sets of detectors on this side?
Okay, there is a way I said if particularly I want to know whether there is a detection for this side and the other side. There's a way I do it particularly, but I have not ascertained today particularly done it. I can have another output from the first AND gate and connect it to the NMI, and another one for the second AND gate. So particularly, you see the difference in the count rates, and maybe you can see even there is one that have a higher count than the other, but the final count is the one that rhymes for the two sets of data. Yeah. So basically, this one is already a two-fold coincidence set. So there is no any other count for the other two that are.
Okay, well, thank you very much. If there are no further questions, are there any questions online? Are there any questions? No, I don't think. Okay, then thank you very much. If there are no further questions, thank you very much for this session. We are going to end our session and share the link to the recording. Thank you very much.
Thank you.
Okay, thank you very much. We will end our session now.